Hey folks, I'm recording solutions for problem 43 in chapter 10. It's one of our instructional problems. It reads, you have been hired to design a spring-loaded, a spring-launched roller coaster that will carry 2 passengers per car. The car goes up a 10-meter hill and then descends 15 meters to the track's lowest point. You've determined that the spring-loaded car will have a maximum mass of 400 kilograms. For safety reasons, the spring constant should be 10% larger than the minimum needed to get the car just to make it over the top. So, first part is to draw a picture of the scenario to the right of the prompt. So it's something, it doesn't need to be pretty and it doesn't need to be to scale, but we're saying that we have something like this, right? Boop, boop, boop. So I'm saying that I have an initial starting point with a spring. I have my cart, right? And then I'm going to go up 10 meters. And then I go down 15 meters, which means I'm going down 5 meters to my lowest point in the track, right? So that's honestly a good enough scenario here. I don't know what K is, and I'm unsure. Well, I know something about delta X, right? I know delta X can be 2 meters, and I know something about the mass. It's going to be 400 kilograms. I think this is a good enough picture to keep rolling. So part B. Where would you place the potential energy due to gravity equal to 0? So we got to pick a location where we're going to set our gravitational potential equal to 0. I would say there's two kind of obvious locations that I would pick. One is right, let me change colors here, is right here, right at our lowest point. We could say UG equals 0 here, and then everything is relative to this point. Or we could say that we start with 0 potential energy, UG equals 0 up here, and that way when we actually go down we're at a negative potential energy. That's perfectly fine. I think either way is perfectly reasonable to do. This question does not have a correct answer. I'm asking you to kind of make a choice, defend it with the explain, and I think all these choices are correct. I think even putting it up here could make sense, but I think that that's maybe the least convenient place to put our potential energy equal to 0. So where would I place it? I would probably place it at the very bottom, at lowest point. I would put it at the lowest point because that's 0, right? And then I'm going to have everything be positive for my potential energy. So then because potential energy due to gravity will be positive. So now positive everywhere. Whew. All right. How much spring potential energy do we need to just make it over the hill? And we give a hint. We say, think about how much gravitational potential energy changes. So with this, I would say, we are losing gravitational, we're actually gaining, we're gaining gravitational potential energy here. We need 10 meters worth of gravitational potential energy. So let's think about that, right? Our spring potential, let's call that delta U E for elastic. The change in spring potential here has to give us some kinetic energy. The kinetic energy at this point has to fuel us going all the way up the ramp to our point here where we have maximum gravitational potential energy. So our delta UE turns into a delta KE, which turns into a delta UG in this scenario. Let's cut out the middleman. It doesn't go to 0, sorry. It doesn't go to 0, but let's just cut out the middleman. Let's just make these two equal to each other, all right? Delta UG. Delta UG is mg and then the height difference, right? Delta H, if we will, or delta Y. And we know that this is going to be our 10 meters. We know that our mass is 400 kilograms, and we know g is gravitational acceleration of 9.8. So then on this side, I have 1/2 k delta x squared, right? So, so really, I don't even need to solve this portion yet. I don't need to know what k is. I'm really just saying all of my change in gravitational potential energy is coming from my change in elastic potential energy. So how much spring potential energy do we need? Well, we need 400 kilograms times 9.8 meters per second squared times our 10 meters of height difference there. And if I throw this into a calculator, right, I should get a gravitational potential energy difference of 400 times 9.8 times 10 gives me, I get 39,200 joules worth of energy. So that is how much spring potential energy we need as well, right? That's just to get over the top of the hill. So if we go to the next part, what spring constant should we report then? Remember that we want 10% larger than the minimum value. Well, we know that we have 1/2 k delta x squared, and this is where we are going to equate that equal to 39,200 joules. And when we do, we can double that. And we can divide by, we said it was 2 meters. Yes, maximum 2 meters of compression. So we'll double it and then divide it by 2 twice because it's squared. We get a k value equal to 19,600 newtons per meter. And this is a reasonable spring constant for something that is going to essentially propel a cart through a roller coaster. Shocks on a car, that has a spring constant of somewhere around 100,000, somewhere between 10,000 and 100,000 newtons per meter. So this is somewhat reasonable. I think the only other thing we need to remember, though, is that we want 10% larger than the minimum value. This is the minimum value, right? So if this is our minimum value, the k reported needs to be 19,600 times 1.1, right, to give me that 10% bump. If I do that, 19,600 times 1.1, I get 560 newton per meter. And so that is the value that we want to report. The last part, the roller coaster cars have been manufactured lighter than expected. Oh no. How fast does a 350 kilogram car go at the bottom of the hill, assuming the spring has been compressed the full amount? So the funny thing here is so we're going to assume, right? We're going to assume that we have a k value that we've reported. So k equals to 21,560 newtons per meter. I'm still going to use a delta x of 2 meters, but my mass now is 350 kilograms. And if we go back to our picture here, I have some initial setup that I need to talk about, and this is going to be my final point, right? My final consideration here. I actually don't need to worry about the hill. We're going to see that in just a second. If I think this through, I know that the change in kinetic energy here plus the change in all my potential energies, so my elastic plus my change in gravitational, need to equal 0. They don't equal any work because we're assuming that we're on a frictionless track here. We would say that there's some sort of friction in the system if we couldn't assume that. And so what I'm saying is, what's my kinetic energy initial? What is my gravitational potential initial? What is my elastic potential energy initially? Right? That should all then equal KEF, my final kinetic energy, my final potential energy due to gravity, and then my final potential energy due to spring forces. So what do I have initially? Initially, I have some spring potential energy. If we've set our potential energy due to gravity at 0 at the bottom here, that means I also start off with some delta. I have some gravitational potential energy. The thing I don't have at the beginning is any kinetic energy. And so this goes to 0, and these two remain. So I have mgh initial plus 1/2 kx squared initial. What does that equal? Well, we've defined our potential gravitational energy to be 0 at the bottom, and there's no springs over here, so there's no compression of the spring before, so it's really just equal to 1/2 mv final squared. Everything else went to 0. And so, like I said, it almost doesn't even matter that I have that hill to begin with, right? I'm just looking at my initial and final points here. So I have some mass. Unfortunately, mass is not constant throughout each of these terms. It's not present in each of these terms. So I have 350 kilograms times 9.8 meters per second squared times my height. My height is going to be 5 meters. It's only 5 meters, right? I start out 5 meters above my 0 point. And then I say plus 1/2 k, which we said before was 21,560 newtons per meter, times 2 meters squared. And we're trying to find our velocity here. So let's divide that by the mass. Let's divide that by half the mass, I suppose. 1/2, 350 kilograms. And then, of course, we'll need to square root the whole thing to get our final velocity. So if we do that, square root 350, I need a parenthesis there, 350 times 9.8 times 5 plus 0.5 times 21,560 times 2 times 2 divided by 0.5 times 350. That's in a parentheses. Make sure you have all your parentheses set, otherwise you're going to have a bad day. And I get 18 meters per second. Really, it's, I suppose, 18.6 meters per second for this velocity of the cart at the bottom of the hill, assuming that it's a little bit lighter than what we had before. So that's this problem. If you have any questions, feel free to email me or come to an office hour. All right. See you later. Bye.